Now we are in a new step, data preparation. Data preparation, often referred to as the ETL process, extract, transform, load, comes next. This involves cleaning the data, transforming it into the necessary format, and storing it in a single location. This preparation ensures that the data is accessible to machine learning engineers, allowing them to build effective models. In data preparation process, we focus on filtering out irrelevant data, removing extreme values, and ensuring that each data column is correctly formatted. Additionally, we conduct exploratory data analysis to identify patterns and prepare a final version of the data for modeling. Now, let's take a quick look at the structure of our data. We can start by checking the first 5 rows to see what the data looks like. We do this using the DataFrames head method. Here's how it works. This line of code will display the first 5 rows of our dataset. It helps us understand the columns, data types, and any patterns in the data. This step is important to get familiar with the information we're working with. Next, we can use the info method to get a quick overview of our dataset. This command will show us the total number of rows, each attribute's data type, and the number of non-null values. For instance, our dataset has 20,640 instances, which is quite manageable for machine learning tasks. However, I noticed that the total underscore bedrooms attribute only has 20,433 non-null values, indicating that 207 entries are missing this information. We'll need to address these missing values later on. Looking at our dataset, we see that all attributes are numerical except for ocean underscore proximity, which is of type object. This typically means it holds text data since we loaded it from a CSV file. To explore the categories within ocean underscore proximity and see how many districts belong to each category, we can use the value underscore counts method. This command will provide a count of instances for each unique value in the ocean underscore proximity attribute, helping us understand the distribution of this categorical data. Now, let's examine the numerical attributes with the describe method. This will provide a summary of the numerical fields in our dataset, including count, mean, min, and max values. Note that null values are ignored. For example, total underscore bedrooms shows a count of 20,433 instead of 20,640. The output also includes the standard deviation, STD, which indicates how spread out the values are. Additionally, you'll see the 25th, 50th, and 75th percentiles, often referred to as the first quartile, median, and third quartile, respectively. For instance, 25% of districts have a housing underscore median underscore age less than 18, 50% are below 29, and 75% below 37. This gives us a good understanding of the distribution of values in our dataset. Another effective way to understand our data is by plotting histograms for each numerical attribute. A histogram visually represents the number of instances on the vertical axis that fall within specific value ranges on the horizontal axis. We can plot histograms for individual attributes, but we can also use the hist method on the entire dataset to generate histograms for all numerical attributes at once. This code will create a histogram for each numerical attribute, allowing us to quickly assess the distribution of values across the dataset. It's a great way to identify patterns, skewness, and potential outliers. Next, we should create test sets and train sets. To split our dataset into training and testing subsets, we can use the train_test_split function from scikit-learn. This is a straightforward way to ensure our model can be trained and evaluated effectively. In this code, housing is our original dataset. Test_size equals 0.2 indicates that 20% of the data will be allocated to the test set, while 80% will be for training. Random_state equals 42 ensures that the split is reproducible. Using the same seed will give the same results every time. This division allows us to train our model on one part of the data and validate its performance on another, unseen part. Let's examine this in detail in the next part.